Hello, everybody. So let's go ahead and get started. So we have, starting with the multiple choice questions, some nomenclature. So what I want you guys to do is find the parent first. So we want to recognize which groups can be part of the parent, and then we want to know how that would be named, right? So I'm circling all the different mono-substituted aromatic rings that have a parent name. So then the groups that I'm not circling then are substituents. And carbon number 1 will always be the carbon that has the group that's part of the parent, right? So this becomes 1, 2, 3, 3 chloro. And then we have to know that this is called styrene. Over here, this would be carbon 1. So it's 1, 2, 3, 4, 4 nitrobenzaldehyde. And then here we have 2 substituents. We want the lowest number possible for the first substituent. So we're going to count in this clockwise direction. 1, 2, 3, 4. This is an ethyl group, which starts with an E. This is a bromo group, which starts with a B. So alphabetically, B comes before E. So we need to write 4 bromo, 3 ethyl, and then the parent name, which in this case is anisole. Over here, this is carbon 1, and no matter which way you count, it's going to be a 3, 5 dimethyl, and then the parent name, which is aniline. All right, question number 2 talks about the energy diagram in your book for the heat of hydrogenation of cyclohexene, cyclohexadiene, and benzene, and it asks us to explain the unexpected stability of benzene. So this talks about the fact that the hydrogenation of one alkene in cyclohexene gives us a delta H, which is negative, and specifically gives off 120 kilojoules per mole of energy. So this is an exothermic reaction because delta H is negative. So if we take this and multiply it by 3, because there are 3 pi bonds in benzene compared to 1 pi bond in cyclohexene, we would expect 3 times this number. So 120 times 3 is our expected delta H of negative 360 kilojoules per mole. But what we see is that we have an observed delta H of negative 208 kilojoules per mole. So hydrogenating benzene is still exothermic, right? But it gives off a whole lot less energy than expected because benzene has aromatic stability, right? So our explanation is, right, 3 times the expected value for 3 pi bonds, right? And then we have our observed, which is 152 kilojoules per mole less than expected, right? So this is the aromatic stability. All right, so the next question, of which there will be multiple on the exam. So this is substituting for question 3, 4, 5, 6, and 7. And it says, assuming coplanarity of adjacent p orbitals, select either aromatic, anti-aromatic, or non-aromatic for the following compounds. Clearly explain your answer. Label if each atom in the ring has a p orbital. If there's a lone pair, explain if the lone pair is in a p orbital or a hybridized orbital. So coming around here, we have pyridine. Pyridine has multiple pi bonds. So there's p orbitals everywhere there's a pi bond. And then the third pi bond here also has 2 p orbitals. But that means that this lone pair is not in a p orbital. So there is a p orbital all the way around the ring, right? And with 3 electron pairs that are located inside those overlapping p orbitals, 1, 2, 3, this is an odd number, right? So this is aromatic. And the lone pair, right, is not in a p orbital. This lone pair is in an sp2 hybridized orbital. So what we want to remember here is that when we have an atom that has both a lone pair and a pi bond, the p orbital that might participate in aromaticity is the pi bond. The lone pair will be in a hybridized orbital. Taking a look at this one, right, we have the same situation where there's a nitrogen here with both a lone pair and a pi bond. The p orbitals are from the pi bond, which means that this lone pair, right, again, is part of an sp2 hybridized orbital, and it's not in the p orbital, so it doesn't count towards the aromatic number of electrons, or in this case, potentially anti-aromatic. Let's go ahead and take a look. So whenever you see a carbocation, there's an empty p orbital, right? Empty means there's no electrons in it, but there's still a p orbital there. So there's a p orbital all the way around the ring. And if we count up the electron pairs in those p orbitals, we have 2 electron pairs, right? So 2 electron pairs means anti-aromatic. And again, it's 2 because only the 2 electron pairs in the 2 pi bonds count, right? This lone pair is not in a p orbital, so it does not count. And this p orbital doesn't have any electrons in it. And the reason why we're going to call it anti-aromatic is because, remember, we're assuming coplanarity of adjacent p orbitals. So if there's an even number of electron pairs in those, we have to call it anti-aromatic. For this one, it would be useful to draw resonance. So we know that with carbonyls, there are 2 significant resonance contributors. Right, so this is another resonance contributor. And as we can see here, we have a pi bond. So there's 2 p orbitals on those 2 carbons. And then again, a p orbital here that is associated with a positive charge, so it's an empty p orbital. The electrons in both the sigma and the pi bond here spend most of their time around the oxygen. So we can basically say that this carbon is electron deficient and has a significant amount of positive character. So now we have a p orbital all the way around the ring. We have to assume it's coplanar, which means depending on the number of electron pairs, it's either going to be aromatic or anti-aromatic. There's only 1 electron pair. 1 is an odd number. So this is aromatic. Again, we don't count the electrons in the pi bond because they're primarily outside of the ring on the oxygen atom. Coming over here, we have p orbitals at those 4 carbons, right? But this carbon here does not have a p orbital. It's sp3 with 4 bonds attached. So with no p orbital there, we have to call this one non-aromatic. Coming over here, we have a bicyclic compound. there is a pi bond associated with every single carbon. So there's a p orbital at every single carbon. We assume they're coplanar. So now we're going to count up the electrons and either call it aromatic or anti-aromatic. So we're counting up electron pairs, 1, 2, 3, 4, 5, right? 5 electron pairs. 5, again, is an odd number. So this is aromatic. All right. Moving on to the next question. Explain whether the following lone pairs are participating in the aromaticity of the ring. What orbital is each located in? So we are looking at each one of these lone pairs, right? As we know, the p orbitals are associated with the pi bonds. So we've now looked at several examples here where when you have an atom with both a pi bond and a lone pair, right, the p orbital that's on that nitrogen, right, is from the pi bond, which means that this lone pair is in an sp2 hybridized orbital. This nitrogen does not have a double bond, it only has a lone pair. So if we put this one in a p orbital, then there will be a p orbital all the way around the ring, and there will be 3 electron pairs in those p orbitals because we have this one, that one, and the lone pair, right? So this lone pair is participating in the aromaticity of the ring, and it's located in a p orbital, right? This one is not participating in the aromaticity of the ring, and it's located in a hybridized orbital. This one is clearly not part of a ring, right? So it's not participating in the aromaticity of the ring. And because this nitrogen has 1 lone pair and 3 bonds, it has a steric number of 4, it's in an sp3 hybridized orbital, right? So we'll make some notes here. This one is participating in the aromaticity of the ring, right? And these two are not. All right, moving on to the next question. Identify which compound is expected to have the lower pKa, i.e. be more acidic. Explain your choice. Right, well, we want to draw in some available hydrogens here, and I'm going to focus on these carbons. You could think of any one, but typically hydrogens attached to an sp2 hybridized carbon are not going to be very acidic. So if we think about these acting as an acid, that means that they can lose a proton to become the conjugate base. So if some base comes in and takes one of these protons, right? So you can think of some base coming in to take one of these protons, right? Same thing, same idea with any of these. We're not being specific about the base, just any base. So what's going to form here, right? We're going to form the conjugate base. So we want to draw that. So we have a 5-membered ring here. Now we have a lone pair and a negative charge. We have a 6-membered ring with an oxygen in it. We have another lone pair and a negative charge. And again, another 6-membered ring. So these are our conjugate bases, right? And in only one case is this conjugate base aromatic, right? This one is aromatic. These two, right, are non-aromatic because they don't have the right number of electrons in overlapping p orbitals in the ring. So the fact that this is aromatic, right, means it's stable, right? And if this is stable, we would say that this is likely going to be a weak base, which means this is likely the stronger acid, right? It will have the lower pKa, right? And we can say more acidic. All right, the next question asks about benzylic oxidation with sodium dichromate or potassium permanganate, and it asks for some examples of alkyl groups that get oxidized and those that would not react. So sometimes it's just more efficient just to draw one example with a bunch of different groups attached, right? So let's say we had a methyl group, right? Or an ethyl group. We could even have a tert-butyl group, right? Or maybe an isopropyl group. So lots of different examples here. And let's say we treated this compound with excess sodium dichromate, right? Or potassium permanganate. Usually that's done cold with some base around. So we would get oxidation at any carbon that has at least one hydrogen attached. So this one has 2 hydrogens attached. This benzylic carbon has 3, right? And then this benzylic carbon has 1 hydrogen attached. But this one does not have any hydrogens attached, right? So I'm going to write no hydrogens attached, right? So this one has 2 hydrogens, 3 hydrogens, and 1 hydrogen, right, at the benzylic carbon. So we're looking at the what we call the benzylic carbon, which is the carbon attached to the ring, right? And as long as there is at least 1 hydrogen attached, that carbon will get oxidized to a carboxylic acid. Those that do not have one will be unreactive. So that tert-butyl group down here will remain a tert-butyl group. And then we can draw a carboxylic acid at each of these other benzylic carbons. Okay, so I'll make sure to write no reaction here. Okay, whereas all of these, we have oxidation. Okay, moving on to the next question. Fill in the missing reagents. So we have benzene being converted to toluene. In order to add this methyl group, we need to do a Friedel-Crafts alkylation with methyl chloride or methyl bromide and a Lewis acid catalyst. Here we're going to do benzylic halogenation. For that, we do 1 equivalent. We would need to be careful to add only 1 equivalent because there's 3 hydrogens here, which could all potentially be replaced with a bromine. And if we had excess reagent around, then we would get up to the triple halogenated product. So 1 equivalent of NBS, right, or Br2, and typically heat or light is mentioned. Going from the benzylic halogenated product, so in this case, this would be benzyl bromide, doing an SN2 reaction here, right? So this is an SN2 because this is an unhindered primary carbon. We're going to do sodium hydroxide. So SN2 requires a strong nucleophile, so we're using sodium hydroxide. From here, we can oxidize the primary alcohol to an aldehyde using PCC. And we can oxidize the primary alcohol all the way up to a carboxylic acid using sodium dichromate. All right, this is a guide for question 12 and 13 on the exam. Explain which of the following electrons count towards the pi electrons in the aromatic ring. Which don't count and how do you know? How many pi molecular orbitals are formed and how many of those are bonding molecular orbitals? Use a frost circle to predict the energies of the molecular orbitals. So we know that we have a p orbital anywhere there's a pi bond. So we have a p orbital at all 4 of those atoms. Recall that if an atom has both a lone pair and a pi bond, the lone pair is not in a p orbital, right? It will be in a hybridized orbital and does not count towards pi electrons in the aromatic ring. Remember, they have to be in a p orbital to count, right? So, and then up here, we have 2 lone pairs. In order to get 3 electron pairs, we need to incorporate one of those, right? So it doesn't matter which one, we can just pick one, say it's in a p orbital, right? And then the other one then has to be in an sp2 hybridized orbital. We know it's sp2 because this lone pair doesn't count, right? So it has a steric number of 3, the oxygen atom, and therefore is sp2, right? So these 2 do not count, but the other ones do count, right? So the electron pairs that do count are the 2 electron pairs one in each pi bond, and then the lone pair in the p orbital. So, right, so these do count towards the pi electrons in the aromatic ring. So if we think about a frost circle, right, for a 5-membered ring, we want to put one of the point down. I'm not very good at drawing them, but you won't have to draw one on the exam. And then, right, this would be inscribed in a circle. And everywhere the ring meets the circle, there is a molecular orbital, right? And technically, the center of the ring is just above these two molecular orbitals, right? So if we simplify this, essentially we have 1, 2, 3, 4, 5, right? With the center of the circle right here, right? So we have 3 bonding molecular orbitals and 2 anti-bonding molecular orbitals, right? So because we have, right, 3 electron pairs, we know that this compound is aromatic. And those 3 electron pairs are going to fill the 3 bonding molecular orbitals, which is a very stable situation, resulting in the aromatic stability that we note with the lack of reactivity of aromatic compounds. The next question is, which of these substrates would react rapidly under SN1 conditions? So recall that SN1, right, the rate determining step is the loss of a leaving group step, right? So if we draw an arrow, which shows that the bromine is leaving, then we would form a carbocation and bromide. Now, in all of these cases, bromide is going to be the leaving group, and bromide is a good leaving group because it's a weak base, right? And so we really want to just look at the stability of the carbocation. So this is a tertiary carbocation, and we know that those react or form easily, right? So this is considered a rapid SN1 reaction, right? So this one is going to be very, very slow, right? Because if we do the same step, the loss of a leaving group, right? And I should probably write that up here somewhere. So this is loss of a leaving group. We have a primary carbocation and bromide, right? So a primary carbocation will form very, very slowly. So I'm even going to put brackets around this because this is sort of theoretical. This would actually not happen very efficiently in solution. Looking at the last 3 cases, we're really analyzing the same step, right? We are considering the loss of the leaving group and the carbocation that forms in each case. So we would form in this case a secondary benzylic carbocation, which we know is resonance stabilized. Tertiary carbocations are considered to be stabilized through hyperconjugation, right? But because it's benzylic in particular, right, this should also be a rapid reaction. looking at the next two cases, we have a 7-membered ring and a 5-membered ring. And of course, in all of these, we also formed bromide. So in these cases, we're looking to see, right, is this stabilized in any way? Well, we have 1, 2, 3 electron pairs, right? So this is a secondary and aromatic carbocation, right? And this would be a secondary and anti-aromatic, because there's only 2, which is an even number of electron pairs. So we expect the formation of the aromatic cation to be rapid, right? And the anti-aromatic cation to be much slower. All right, the next question says, label the groups in the following 10 monosubstituted benzene rings as strong activators, moderate activators, weak deactivators, moderate deactivators, and or strong deactivators towards a EAS or electrophilic aromatic substitution reaction. So for that, you can actually review the table in your book, right? So if you look here, you can see that we are looking at chapter 18, right? And this is a table that is on page 852. So this labels each of these as strong, moderate, weak activators, right? And then weak, moderate, and strong deactivators. So that's where I'm getting this information from, in case you were wondering. So we can go ahead and label. So methyl groups, right, are weak activators, and halogens are weak deactivators. The book puts the OH group in a phenol in the strong activator category, whereas a methoxy group or an OR group in the moderate activator. But it's very likely to be one of the strongest moderate activator. So it's, very close to being a strong activator. A nitrogen, right, with either hydrogens or methyl groups, if there's 2 of them, right, there's also a lone pair on here. This will be a strong activator because that lone pair is strongly pushing electron density into the ring. Whereas a nitro group is a strong deactivator. This one actually has a positive charge on the nitrogen, so it does not have a lone pair that's pushing electron density in. Instead, it's inductively strongly pulling electron density out of the ring. Looking at the last 4 here, we have a ketone, right? So notice the carbonyl directly attached to the ring. So this is going to be considered a moderate deactivator. Whereas this one has an oxygen with a lone pair right next to the ring. So that's through resonance donating electron density into the ring. So this is considered a moderate activator because the lone pair is partially tied up outside of the ring through the other carbonyl. Again, there's a lone pair on this nitrogen pushing electron density in, but since it's partially tied up in resonance outside of the ring, this is also a moderate activator. And with 3 electronegative fluorine groups, this is inductively a powerful deactivator. The next question is sort of related because it has the same structures, I believe, but asks about whether or not the substrates would undergo a Friedel-Crafts reaction and which would not react. So what we're looking for here is any that are either moderately or strongly deactivated, right? Those will not undergo a Friedel-Crafts reaction. All of the other ones should undergo the reaction. So we have, I don't know how to write this, right, succinctly. We'll just do checks mean it will activated and undergoes Friedel-Crafts reactions. Right, and then we'll do X's mean, right, either moderately or strongly deactivated, right? No Friedel-Crafts reactions. Okay, so we'll put activated or only weakly deactivated. Okay, so all we need are checks and X's, right? So this one, again, is weakly activated. Weakly deactivated is fine. Strongly and moderately activated will definitely work. Here's another strongly activated compound. Nitro groups are strongly deactivated, and this carbonyl is moderately deactivated. Whereas these two, because there's a lone pair directly attached to the ring, these are moderately activated and will definitely work. And then here's another powerfully or strongly deactivated, so no Friedel-Crafts reaction can occur from that substrate. Looking at the next question, draw the product when the following 8 substrates undergo reaction with Br2 and FeBr3. Okay, so I'm just going to go ahead and add in the group attached to this substrate as opposed to drawing this out again. So we just need to know where the group is being directed to. Halogens are ortho-para directors, and they'll direct para first. So we will put the bromine para, right, to the chlorine. Methyl groups are weak activators, also ortho-para directors, so we should put the bromine para first. Methoxy groups are ortho-para directors, para first. This ketone, again, is a moderate deactivator, which means it's a meta director. So we're going to put the bromine meta, and so I'm going to use, when it's being directed to the meta position, I'll use a different color. Right, looking at these substrates down here, the nitro group is a meta director, whereas the dimethyl amino group is an ortho-para director. The trifluoromethyl group is a meta director, whereas the ester with the oxygen attached to the ring is a moderate activator and ortho-para director. We'll put the bromine para. So draw the product when the following 4 substrates undergo reaction with nitric acid and sulfuric acid. So now we have to look at multiple groups and where they're directing. So we have the chlorine directing ortho-para, right? And the para position is blocked. So it's going to direct to these ortho positions. And the sulfonyl group will also direct to the same positions because it's a meta-director. So these positions are equivalent because of the internal plane of symmetry. So we just need to put the nitro group on one of those 2 carbons. Looking at this one, the methyl group is an ortho-para director. It's definitely going to direct para first because this is a much more sterically hindered position, right, than this one. And the nitro group is a meta-director, so it's also directing to this position and this one, right? This one's much less sterically hindered, so we're going to put the nitro group there. Both the methoxy group and the methyl group are activators. The methoxy group is a moderate activator and the methyl group is a weak activator. So we're going to listen to the methoxy group first, right? It's directing ortho-para and the methyl group is also directing ortho-para. So luckily they're directing to the same positions. So we want to place it in the least sterically hindered position, right, which would be this one next to the methyl group. Over here, we have a weak deactivator and a moderate deactivator, but halogens, even though they're weak deactivators, they're ortho-para directors. So it's directing ortho and para first. And then the moderate deactivator is a meta-director. So it's directing to the same positions, this one being much less sterically hindered. We'll put the nitro group there. The next question is, which of these synthetic pathways is more successful? Explain your answer. So we have the direct Friedel-Crafts alkylation or a Friedel-Crafts acylation followed by Clemmensen reduction. So the second pathway is definitely, right, much more successful. And that's because the Friedel-Crafts alkylation is subject to rearrangement. And so the product that's shown is actually not likely to be the major product, right? This is likely to be a minor product. And the major product will be the rearranged product. So we have 1, 2, 3. It will rearrange to a secondary carbocation and introduce an isopropyl group. Whereas the Friedel-Crafts acylation, right, is entirely successful, followed by the Clemmensen reduction. Right, and this one will be the major product. Next, we have fill in the missing reagents and substrates. So we have a 2-step process to introduce a carboxylic acid, right, to replace the hydrogen. So the way we can do that is through introduction of an alkyl group that has at least one benzylic hydrogen, and then it can be oxidized up to the carboxylic acid. So for example, and there's multiple answers here, you could introduce a methyl, an ethyl, an isopropyl, right? Any of those would work. But I'm just going to choose a methyl since that's simple, right? So we introduce the methyl group and then do a benzylic oxidation, right? With oh, where is my brain? Sodium bisulfite. No. I think I've reached my limit here. I think it's Na2S2O4. Just double check that. No, sodium dichromate, sorry, Na2Cr2O7. I'm tired. Okay, Cr2O7. Okay, then from the carboxylic acid, we want to introduce a amino group, meta. Luckily, this is a moderate deactivator and meta director. So we'll be able to introduce a group that we can then convert to the amino group. So the way we get an NH2 group, right, or an aniline derivative is through a nitro. So we can introduce the nitro group and then reduce the nitro group. The reaction to introduce the nitro group is nitric acid and sulfuric acid. And then we reduce the nitro group through using zinc and HCl. And then sometimes it's mentioned that there is a basic workup in order to isolate the free base product. We have another fill in the missing reagents and substrates. So it looks like we are starting from chlorobenzene. We need to introduce a nitro group and a sulfonyl group. So we need to, the chlorine is an ortho-para director, so it's going to direct para first. So we'll put on the sulfonyl group followed by the nitro group. So we have going to target this intermediate. And we'll introduce that with fuming sulfuric acid. And then the nitro group will be directed, right, ortho to the chlorine and meta to the sulfonic acid. And that will be introduced through nitric acid and sulfuric acid. The next part of the synthesis, we want to replace the chlorine with a OH group, right, to make a phenol and remove the blocking group. So we can think about which order we might want to do that, right? At this point, this is a good deactivator, so it's great to have in place for the nucleophilic aromatic substitution reaction. Or alternately, we could remove it first, and even just having the one nitro group ortho to the chlorine would be sufficient. So either really these two reactions, could potentially be swapped. But I think it makes sense to do the nucleophilic aromatic substitution while this is in place, because it will only make the reaction faster, and then remove it in the last step. So we'll target the replacement of the chlorine with an OH group first. So that's our nucleophilic aromatic substitution. And then loss of the blocking group second. But again, these two potentially could be switched. In order to replace the chlorine with an OH group, we need to use sodium hydroxide and heat. Right, and there's an acidic workup in order to isolate the phenol. Right, and then and it's possible that the sulfonyl group will start coming off even in the acidic workup, but if it doesn't, you can do a more prolonged treatment with dilute sulfuric acid to remove it. Determine a multi-step synthetic pathway. So from benzene, we can only access this OH group through a nucleophilic aromatic substitution reaction, which needs to have the nitro group either ortho or para to the leaving group. So the best pathway would be to introduce the chlorine or bromine, so whatever leaving group you're going to use first. Use this to direct the nitro group para. And then now that we're set up nicely to do a SNAR reaction, a nucleophilic aromatic substitution reaction. So we can use chlorine and a Lewis acid to introduce the chlorine, nitric acid and sulfuric acid to introduce the nitro group directed para by the chlorine, and then the SNAR reaction is done through, again, sodium hydroxide and heat and an acidic workup. So really very similar to the last question. Provide the name of the following. So we have both an aldehyde and a ketone. Whenever we have both, we know we're going to name it as an aldehyde because that has a higher priority than the ketone. The ketone will then be a substituent called an oxo group. So this is the only substituent. We have 5 oxo, and then we have 6 carbons in total, right? So this is a hexanal. So it would come from hexane, but we drop the E and we add the Al, so hexanal. Fill in the 2 different conditions to reduce the carbonyl to an alcohol, or 3 different ways to reduce the carbonyl completely to a methylene group. So some of these are review reactions. You might recall that we can use either sodium borohydride or lithium aluminum hydride with an acidic workup to reduce to the alcohol. And then there's 3 different ways you can completely remove the carbonyl. So we can do a Clemmensen reduction, so zinc mercury amalgam and HCl. We can do the Wolff-Kishner reduction, which utilizes hydrazine to make a hydrazone intermediate, followed by treatment with aqueous potassium hydroxide and heat, right? Or we could form a dithiol and then do a Raney nickel reduction. What is a cyanohydrin and how is it formed? So a cyanohydrin is formed from an aldehyde or a ketone being treated with potassium cyanide and hydrogen cyanide. And we get what's known as a cyanohydrin, which could be abbreviated like this, or you could draw this out. And draw in the triple bond here. Right, so you either draw it the abbreviated way or the non-abbreviated way, right? So this is called a cyanohydrin, right? And it can be a couple of different example reactions of a nitrile the book gives for this, right? We can either treat this with aqueous acid or with LAH, right? So if we treat this with LAH and an acidic workup, sometimes people write water or H3O plus, we would get the reduction of the nitrile to a CH2NH2 group, or we could treat this with aqueous acid and we could do hydrolysis of the nitrile to get a carboxylic acid. So this would produce a alpha hydroxy acid. How could you prepare the following compounds via a Wittig reaction? So we could think about making this double bond, and we want to do so in a way that puts the carbonyl on the more substituted side if there's a difference, and the Wittig reagent on the less substituted side, because it has to be prepared through an SN2 reaction. So kind of working our way backwards or retrosynthetically, we would want the Wittig reagent to be on the less substituted side and the carbonyl to be on the more substituted side. Looking at this one, there's a little bit of difference in terms of steric hindrance, whereas this carbon is not as sterically hindered as that one. So again, we'll put the Wittig reagent on this side and the carbonyl containing reagent on the other. Right. Draw the products of the, if the following compounds undergo a Baeyer-Villiger oxidation reaction. So in a Baeyer-Villiger oxidation, these substrates, aldehydes or ketones, are treated with MCPBA, which again stands for metachloroperoxybenzoic acid. It can form epoxides from alkenes, or it can do the Baeyer-Villiger oxidation. And in thinking about where the oxygen will insert, it will insert between the carbonyl carbon and the more substituted carbon, which in this case would be on the right. Again, this is more substituted than that, so it would insert here. And then given that one of them is a hydrogen because it's an aldehyde, it would insert on that side. So we can kind of think about where we want to insert that oxygen and then redraw it with the oxygen there. I'm actually going to draw this with a different color, right, so that it's sort of clear exactly where we want that to go. Kind of a visual cue here. Okay, so we want to do the isopropyl group, right? Then we're inserting the oxygen. Then we're going to come and have the carbonyl, which you could draw this way or you could draw it down, either way. Lastly, we're going to, from an aldehyde, we always get a carboxylic acid. So in this case, we're going to get benzoic acid. We're going to do OH. The next question says fill in the missing reagents. So because this arrow is going up here, I'm just going to start in the middle and then work my way both up and down. So we have, how do we get from a ketone, right, from this carbonyl to this alkene? So we can do a Wittig reaction to do that. So we want to draw the proper ylid with 2 carbons because we're adding 2 carbons. And then we sort of going in the direction moving up, we have the formation of an epoxide. So that would be MCPBA. And then from the epoxide, we learned that we can open up epoxides and put a hydrogen on this less substituted carbon with LAH. Moving down here from the alkene, right, we're doing a hydration reaction because we're adding OH and H. So there's a hydrogen that gets added here, right, and then the OH that gets added here. So this is an anti-Markovnikov hydration reaction. And so we are going to use hydroboration oxidation. So BH3THF, sodium hydroxide, and hydrogen peroxide in the second step. Here we have oxidation of a secondary alcohol to a ketone. So we don't want to forget that we can use PCC or we could use sodium dichromate. Next, we have fill in the missing reagents. For imine and enamine formation, fill in the reagents to go both directions synthetically. So we have, now this is sort of going the opposite direction than we did on the previous question, right? So now we're starting with an alkene and we're cleaving the carbon-carbon double bond to get the ketone. So we want to remember that we can do that through ozonolysis, followed by a reductive workup with dimethyl sulfide. We can form the imine as long as we use a primary amine. So since this arrow is going in this direction, over here, I will put in the primary amine. Right, usually uses an acid catalyst. And we remove water from the reaction. And then to go back, right, we would use dilute H3O plus. For the enamine, to make the enamine, we need a secondary amine. We need an acid catalyst and to lose water. And then to go back from the enamine to the ketone, again, dilute H3O plus. Fill in the missing reagents and structures. So this one might be a little bit tricky at first, but maybe if you stare at it for long enough, you might recognize that this is actually an acetal because we have a carbon attached to OR and an OR, right? So 2 OR groups attached to 1 carbon. So we call that an acetal. So acetal formation is reversible. So if we want to go in the opposite direction, open up the acetal back into the ketone and alcohols, then we're going to use lots of water, right? So we want a dilute acid solution. So you can think of this as the reverse, right, of the acetal formation reaction. And then we see that we want to form a new carbon-carbon bond because we're going to be introducing this methyl group. So we want to do a Grignard reaction, but it's not possible to do that in the presence of the alcohols. So first we need to protect the alcohols, then we can do the Grignard reaction, and then we can deprotect using TBAF, which stands for tetrabutyl ammonium fluoride. So we're going to target the protected alcohols. Right, so we're going to use TMS chloride and pyridine to put those on. And we'll need at least 2 equivalents because there's 2 alcohols that need to get protected. Now that these are protected, we can do the Grignard reaction. So we can treat this with methyl magnesium bromide, right, to do our Grignard. And followed by water or dilute H3O plus. This Grignard reactions form alcohol products, so we'll get this tertiary alcohol. And then TBAF will deprotect those TMS groups to go back to the alcohols. Now we're on the guide to the short answer questions. And this one says, show how frost circles can be a tool to predict MO or molecular orbital energies. To explain why one of the compounds below is aromatic and the other is anti-aromatic, given coplanarity of adjacent p orbitals. Okay, so first we want to think about the fact that we are going to be placing all of these electrons, right, into the molecular orbitals. So we have 1, 2, 3, 4, 5, 6, 7, 8 electrons here, and 1, 2, 3, 4, 5, 6 over here. So if we do 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6, 7, 8. Right, so this shows us that this compound is aromatic, right? Where this one is, anti-aromatic. But we only call it, right, anti-aromatic if, right, if this lone pair goes into a p orbital. So it's a big assumption because, of course, it can also go into a hybridized orbital, right? So we'll put actually goes into an sp3 hybridized orbital, right, to make this compound non-aromatic. However, we're just kind of looking at what it would look like if it went into a p orbital, right? So if it goes into a p orbital, then it would be anti-aromatic and it would have this diradical like instability, which is why it doesn't do that and actually becomes non-aromatic. Whereas this one will definitely go into a p orbital, right? And as a result of it going into a p orbital, we get a nicely stable system with all of the bonding MOs filled. One of the lone pairs below is in a p orbital and the other is in an sp3 hybridized orbital. Draw the resonance contributors of the one that exists in a p orbital to show how the lone pair is fully conjugated and delocalized over every atom in the ring. So we showed from the previous question, right? That this compound was the one that was aromatic, right? And this one is non-aromatic because that's more stable than being anti-aromatic, right? So this lone pair is in a p orbital, right? And this lone pair is in an sp3 hybridized orbital, right? So this one, because it's not in a p orbital, there's no resonance stabilization. Whereas this one is resonance stabilized. Okay. So we want to draw the resonance contributors from the one that actually shows resonance stabilization. And to do that, it's very useful to label your carbons, right? So if we just do 1, 2, 3, 4, 5, right, I can place my pi bonds here, start with my lone pair on carbon number 1, just like it shows up here. And then I can move this as an allylic lone pair, right, all the way around the ring. Don't forget to use your resonance arrow when you do this. So we're going to move the pi bond here, the lone pair here, and we're just going to label these just like they were before. So we move the lone pair from carbon number 1 to carbon number 3. Then we're going to keep going, and it's going to move to carbon number 5. So now we're on carbon number 5. We're going to keep going. Carbon number 2. So far, the lone pair has been on carbon 1, move to carbon 3, move to carbon 5, and it's about to be on carbon number 2. And then we just need to get it to carbon number 4, and then it will have been at every single atom in the ring. All right. Right, and make sure we understand that if a lone pair participates in resonance, it is in a p orbital. Let's draw the mechanism for this Grignard reaction. So I'm just going to redraw the ketone. And I'm going to draw in the Grignard reagent. Remember that the carbon here is both nucleophilic and basic. So these electrons, which primarily reside around this carbon, right, are nucleophilic and they can attack the electrophilic carbonyl carbon. And we need to show a resonance arrow to avoid exceeding the octet on that carbon. So this question really comes from the previous section, right, of the class, but a lot of people struggled with drawing the mechanism for the Grignard reaction in the last exam, so I'm putting it on this exam as well. So we have the oxygen with now 3 lone pairs and a negative charge, and we've added in this aromatic ring. And then in the next step, we're introducing H3O+, which is an acid. And we want to show proton transfer. Remember that we start with the base, pick up the proton from the acid, and leave the electrons behind to form the conjugate base. Now we just need to draw in the product, a neutral OH group, right? And water as a byproduct. All right. Provide the curved arrow mechanism for the following EAS reactions. So let's start with the formation of the active electrophile. So we have the alkyl halide reacting with aluminum trichloride. The lone pair will attack the empty orbital on the aluminum. This is considered a Lewis acid-base reaction to form the complex. Right, the same thing will happen with this alkyl halide down here. Let's go ahead and draw that at the same time for the purposes of compare and contrast. So we're going to do the same reaction. But the difference is that this was a primary alkyl halide. And this is a tertiary alkyl halide. Okay, with the tertiary alkyl halide, we can go ahead and do loss of a leaving group because it's going to form a stable carbocation. Right, but with the primary alkyl halide, we don't want to draw that because we never form primary carbocations. So instead, we'll just start the EAS reaction from this substrate. So I'm just going to go ahead and place a box around this and call this the active electrophile. Right, whereas here it would be the carbocation. So it's sort of like the difference between an SN1 and an SN2 reaction. With a tertiary substrate, it will undergo SN1. So we'll have loss of a leaving group before the nucleophilic attack. Here we're going to do the nucleophilic attack and the loss of the leaving group in the same step, like an SN2 reaction. So that's the difference, right? I'm going to go ahead and draw the aromatic ring in here as well. So regardless, right, we're going to have the nucleophile, which is the aromatic ring, attacking the electrophilic center, right? So this is doing a nucleophilic attack. But here it's going to do the nucleophilic attack and we'll have the loss of the leaving group occurring in that same step. Right, so this is SN2 versus SN1. So we're going to have, we've now taken this, right? It's attached or bonded to the ethyl group, right? I use this pi bond, so I'll just put the ethyl group here. Doesn't matter where you put it. That means that the other two pi bonds I didn't touch, right? And the positive charge will be the carbon that lost the electrons. So it will be this one, right? Same thing here. We're going to draw the aromatic ring, which has temporarily lost its aromaticity. I'm going to put the tert-butyl group here, positive charge there, right? And all we need to do now is to regenerate the aromatic ring in both cases. And to do that, we can just use some chloride since we'll have that around. So I'm just going to draw some chloride, or you can also take it from AlCl4. Here and here. So we want to do acid base, right? So chloride takes the proton, electrons come down to regenerate the aromatic ring. Chloride takes the proton, electrons come down to regenerate the aromatic ring. And we get the product now, right, which is the ethyl benzene in this case, and the product over here, which is tert-butyl benzene. All right, the last one is a little bit different because this is a Friedel-Crafts acylation reaction. So that works similarly, but there are some differences as well. So we're going to start with the acyl halide reacting with the aluminum chloride. Still going to take a lone pair from the chlorine and do a nucleophilic attack. Right now, this leaves the positively charged chlorine right there. Hopefully this computer will focus on it. Does not want to, oh, here it goes. Okay, perfect. Because I want you guys to make sure you're able to see this, right? So we're going to do loss of a leaving group. That is going to form the aluminum tetrachloride byproduct. And then we will form the active electrophile, which is resonance stabilized. So I'm going to draw in brackets my resonance arrow. And then because I'm forming a triple bond here, I'm going to draw this in a linear fashion. Right? And we call this the active electrophile, which is known as the acylium ion. Now the aromatic ring gets involved. You can take any one of those pi bonds, right, and show the nucleophilic attack. If I'm going to bond it to this one, that means this one is positively charged. And we just have our final step to regenerate the aromatic ring. And the product. All right, I have a last question here. Show a curved arrow mechanism to form the acetal below. It should be 7 steps. Label the hemiacetal intermediate. All right, so if you don't have lone pairs drawn in, you make sure to add those, right, so that you can draw the mechanism properly. So the first step we want to do is protonate the carbonyl. Of course, the alcohols can get protonated too, right? But protons come on and off of these things, and eventually we can protonate the carbonyl, which leads to further reaction, right? So first we're going to do, and all of these steps are reversible, right? First we're doing a proton transfer. And we want to draw the product here. Now we can do the nucleophilic attack, right? So now that this carbonyl is protonated, this carbon has a much more significant positive charge. So it's ready to be attacked by one of these alcohols, and doesn't matter which one that you choose. Right, so we're going to show the nucleophilic attack step. That's step 2. So it said it wants 7 steps, so we might even number these, right? Number 1, number 2. We're going to be generating this 5-membered ring here. So 1, 2, 3, 4, 5. Right, so I'm going to kind of make it look like the product to keep myself on track here. This OH, though, is going to still have a hydrogen attached. And then this became an OH group. And this carbon still has a 1, 2, 3 methylenes, 1, 2, 3, right, followed by an OH group. Okay, so now we would like to lose this OH group as water, but before we can do that, we need to deprotonate this and then protonate this so it's a good leaving group. So we want to take something and deprotonate this. You could use anything in solution to do that, right? Or if you don't want to show something acting as the base, you can actually just draw the arrow like this. Basically is the proton pops off. So it's showing proton transfer without actually showing the base. We're finally at the neutral intermediate. And so this is the hemiacetal. So it's the one with no formal charges. Next, we want to protonate this. So if I don't want to draw an acid out, I can just simplify by writing H3O plus or H plus. Again, the point of this is to show a proton on here so that this becomes a good leaving group. Now this is ready to leave, right? Because once it leaves, it will be stable, it will be water. You can either draw just this arrow and put the positive charge here, or you can take this lone pair, do a resonance arrow to help kick out the water. Either way, it results in just different resonance structures drawn, which doesn't matter. So step number 5 is loss of a leaving group. And the leaving group is water. I opted not to draw the resonance arrow, so I'm just going to put the positive charge directly on that carbon, which makes it easy for me to see why there's a nucleophilic attack. And this is forming a 1, 2, 3, 4, 5-membered ring. So step number 6, nucleophilic attack. We are almost at the product. All we need to do is one more final proton transfer. So I'm just going to show that proton popping right off. Right, to form the product and regenerating either H plus with water, which is really H3O plus, right? So we only need catalytic acid because it gets used and regenerated in the last step. All right, that was the end of the mastery assignment. Let me know if you have any questions.